All right, we're good. All right, so guys, like I just said, chapter 3, section 2, we're going to split it down into 2 parts. All right, part 1 today, part 2 tomorrow. Test on Friday will be the stuff we talked about yesterday. On Thursday, I'm sorry. Test on Thursday, so 2 days from now, will be on identify the domain and the range based on maybe a list of numbers. Identify domain and range based on a table, input, output. Identify domain and range based on the bubbles with the lines coming out. We'll do all that. Find domain and range with a chart. Identify whether it's a function or not. All those things that we covered yesterday will be on the test on Friday. This stuff we do today will be on the test on Thursday. And then the stuff we do tomorrow, obviously, will be on the test on Thursday. Tomorrow night, same deal. Go on the Google Classroom. The reference sheet will be on there. Fill it out. You can use it on the test on Thursday. If you think it's going to be a problem for you to print your reference sheet off of Google Classroom, most of you guys bring it already, but bring your Chromebook with you tomorrow. If you don't already bring it on a regular basis, make sure you bring it with you. And we'll try to give you guys some time at the end of the class tomorrow so you can have some time to print it here. It's going to be a problem to print it at home. All right, so chapter 3, section 2, part 1. I'm going to talk some more about linear functions. All right? So a linear equation, it can be in 2. We're going to have 2 variables. Remember, variables are letters. All right? We're going to have an x and a y. And it's going to be written in a certain form. So on your notes, you see a little y equals. Someone tell me by raising their hand. What do you think we're going to write on that line? Something you probably covered last year, the year before, previous years. Josh, what do you think? Y equals mx plus b. Absolutely. We're going to write it in the form y equals mx plus b. So on your little line there, you want to make sure that your m is directly on top of that arrow, x right next to it, write in your plus sign, and then you have room for make sure you put your b directly underneath the arrow. Now, in this formula, does anybody know what the x stands for? Anyone knows what it is? What do you think? Slope. All right, let's take a look and see what we got. Slope, and then my b is y-intercept. Right? So we just wanted to, we're not going to get too much into where you got to start at, you got to start at the y-intercept and then go up 3 over 1. We're not going to worry too much about that. We just want to show you this form because this is what makes it a linear equation. We have a y, we have an x, and we could have some other numbers. But there's no, square roots. There's no exponents. There's no exponents that are variables. Any of that stuff. We're showing you guys this form because this is the form of a linear equation. This is how it has to be set up, right? Because later on in the lesson, we're going to give you different types of equations and ask you to identify whether it's a linear equation or not. So that's why this form is so important. All right?
Do you guys know what that means? What does it mean if it's linear?
Think about linear. What word do you hear in linear?
Line.
Liam. Line, right? So if I have a linear function or a linear equation, it's going to make a straight line. Yeah, like Liam just said, it's going to make a straight line. That's going to be a linear function, and it's going to be it has to be written somewhere along the lines of this form. All right. We got to make sure underneath that you have the 2 little bullets like we just talked about. The graph is going to be a straight line. No curve, no bell curve, no squiggly lines. It's going to be a straight line. It could go straight across like this. Could go straight up and down like that. Those are still straight lines. Those are still qualify as linear functions. All right? So a linear function is a function whose graph is a non-vertical line.
So vertical lines, remember, those are not functions. Horizontals are okay, but vertical would not.
So straight up and down like this? No. Going across is okay, up and down, not okay. All right, so a linear function is a function whose graph is a non-vertical line.
And why is that?
Mr. Hager, you want to take that question?
Why can't it be vertical?
Yeah.
Because remember, what did we talk about yesterday? What test?
Oh, you're right. If we had our graph side, every point here would be hitting on the x-axis. Mr. Hager's going to show you.
So remember that test where we take, thank you. Let's say we had a line right there, okay? And I asked you, is that a function? Okay, what's the test we use? What's it called? Vertical line test. So take a vertical line and start dragging it through. And we're going to check. Does it ever hit my graph more than once?
Yeah.
Oh yeah, it hits it a lot. So because this fails the vertical line test, that's why it's not a function.
I'm confused.
Well, think of it this way too, right? So let's say we got 1, 2, 3, 4, 5, 6, 7, right? My x coordinate is set. My x coordinate is 7. I could pick. Here's a point right here. That'd be 7, comma 1. If I pick the point above it, that'd be 7, comma 2. If I pick the point down here, we'll call that 7, comma negative 2. Uh-oh. I got repeats in the domain, right? I can't have that, right? If you can't see it visually, that's another reason why, because the domains or the x coordinates are going to repeat.
This is so weird. This is the first time I've understood something so completely, but still been so confused.
Okay. I hope that helped a little bit.
It did.
That's a good way to look at it with the numbers, like Mr. Roy just showed.
All right. So we talked about that. It's going to be a straight line. It's got a constant rate of change. That's what, when we talk about slope, that's what slope is, right? It's rise over run. You go up an equal amount, you go to land on a spot in that line, you go up an equal amount, you go over an equal amount. You go up an equal amount, you go over an equal amount. Same thing with a linear function. When it increases, all right, it's going to increase by an equal amount. So it'll be added by an equal amount. All right?
Does everyone understand something that would not have a constant slope? Can anybody think of a picture where the slope doesn't stay the same? With a line, it always does. Yeah? Exactly, something that's nonlinear. Here's an example of something where the slope changes. How can you tell? Like, pretend you were standing right here. If you were standing there, how steep is it right here? It's pretty flat right there. But what if you were standing here?
I fall.
Fall, it's a little steeper. And how about if you were standing here?
You're kidding.
It's even steeper. So this is something that does not have a constant slope because it's curved.
Next thing. Like Mr. Hager just said, a nonlinear function, so that means it's not a straight line, all right? Then it does not have a constant slope, so that rate of change is not the same, and therefore the graph is not a line. So, like Mr. Hager just added some examples. Here's an example of a linear function. It's a straight line, right? We get a constant rate of change. That would work. This, we get a little bit of curve to it. So it's not like Mr. Hager said. Here you start out pretty flat, but then you get more and more steeper, right? But it's not the same amount every time, right? So we got linear, nonlinear. Linear basically says it's got to be a line. The only thing is, the line can't be vertical. All right? Nonlinear, it's gonna have a bend to it, it's gonna be squiggly, basically anything that's not a straight line. Unless obviously, like we talked about, if it's vertical, then obviously it's not that doesn't work for a linear function. Everybody have this?
Yep.
Next. Oh, got my little thing there. All right, so first graph. Guys, it doesn't have, on your thing you just have blank graphs. Draw this in the best that you can. It doesn't have to be absolutely perfect. We're not going to have to ask you guys to identify any coordinates on there. All I want you to do, all Mr. Hager and I want you to do is just draw that the best that you can. It doesn't have to be perfect. So this guy right here, Ariel, is this a linear or non-linear function? Why is it nonlinear? Yeah, it's not a straight line, right? It's got a bend to it, right? So this is going to be right next to it or below it, somewhere near, just write non-linear. So example A is going to be nonlinear, right? Reason being, like Ariel said, it doesn't have a constant rate of change, or we could just say it's not a straight line. So A is nonlinear. Next one, B. Emily Bonka, is that going to be linear or nonlinear?
Linear.
Linear, why?
Because it's a straight line.
Yeah, it's a straight line. And it's not, but don't get tricked. The one tricky thing is, if it's vertical, up and down, right? The long way. That's the one exception to the rule. Right? That's like size rule. Remember, we had to, I think of that like your rule, because we had to go over it for you because you didn't understand it. I'm going to call it size rule.
I just felt
All right,
really
so that's,
stupid.
you're not stupid. Yeah, I forgot too, so don't feel bad. This is linear because, again, it's got that, it's a straight line, it's got that constant rate of change. So that would be linear because it's a straight line. Got it? So example B would be linear. Let's look at C. Liam. It's going to be linear, right? Because this is horizontal, right? This is horizontal. If it's horizontal, right, the x's won't repeat, right? The x's are going to be different every time. It's only when it's up and down, when it's vertical. That's the special case. That's when it will be nonlinear, or it won't be a function. This guy is horizontal. It's okay. That works. So this will be linear.
You just said it's not linear.
This is linear. I said it was linear. I said linear. I know it's getting late in the day, and I was up late last night, but
I'm
I know I said
sorry,
linear.
I'm so out of it today.
All right, so this is going to be linear. All right, again, if all my x's are different, and if I did the vertical line test, I'm not going to overlap at all. All right, I'm not going to hit twice. I'm only going to hit one time every time I pull it through. So that's going to be linear. Example D. Tristan, is that going to be linear or non-linear? Non-linear, right? It's not a straight line. I mean, we have a couple kind of like one line, kind of half a line going here, half a line going here. But it's not a straight line. It's got like a zigzag to it. So that's going to be non-linear.
You know, I'm still counting the boxes and lining it up exactly, even though you said not to. Why?
This is how psi is. It's okay. All right, so D, non-linear. So basically, if it's not a straight line, non-linear. The word is in there, line. So if it's not a straight line, then it's non-linear. If it's a straight line, it's linear, unless it's unless it's horizontal. Good, Liam. All right, so non-linear for D. Mr. A, I don't know what you wanted to do. I'm going to have you do this.
Right, so everybody seems to have kind of a pretty good idea of how to tell if something is linear or nonlinear looking at a picture.
Guys, this isn't on your notes. Just kind of follow along here, okay? It's not on your notes.
So now, we're going to figure out how to answer questions like this. Is this linear or nonlinear? We don't have a picture anymore. All we have is a table. Same thing here, here, and here. Okay? So you could make a picture of it, but there's a way to just look at the table without the picture, and that'll save us time. So let's look at something that is linear. Okay? Let's make a table for some of the x's and y's, and let's see if we can figure out a pattern. Okay? A pattern that happens when something is linear. Okay. First, what I'm going to do is just mark what I think are some nice coordinates on here. So let's mark a few. Okay, how many do I have room for in my table?
A lot.
1, 2, 3,
4, 5.
5? All right, so let's pick this one and one more. This one. All right, so I've marked 5 points. Let's write the coordinates of each of those points. Let's call them,
A, B, C, D.
yes. What's the coordinates of A?
Negative
-2,
Negative 1.
-1.
You guys don't even have to write this down.
How about B?
Negative 1, +1.
-1, How about C?
0, and then +3.
0, +3. D?
+1, +6. Wait, 5.
And E?
+2, times 7.
7. Okay. So now we're just going to look at that list of numbers. Okay. First, everybody agrees that this is linear, right?
Yep.
All right. So we know that this table is linear. It has to be because it came from that picture. So let's look for a pattern. Okay. Let's see if I can take this table and maybe make
All
a
those boxes make that.
copy. See if this works. Paste. Good enough.
Oh, it worked.
Yes, it did. All right, so start with your x's. Does anybody see a pattern in how the x's are increasing? Like how did we get from here to here, here to here?
+1.
Yeah, each time we're doing a +1. So that's the first thing we want to look for. Is there a pattern in the x's? Okay, and yes, in this time there is. It's +1. Now here's the big thing. Do we have a pattern in the y's? And it has to be a pattern where you add or subtract each time.
Yes. +2.
+2, +2, +2, +2. All right? So because we have a pattern where you're adding 2 each time, that is how you tell if something's linear. Okay? The pattern has to be addition or subtraction. If you had something like this, okay, I'm just going to make a little shorter table. Okay, how am I getting from here to the next one each time? +1, so that's good. The x's have a pattern, but watch what I do to the y's. There's a pattern there. Does anybody see what I'm doing? Timesing by 2. Is that adding or subtracting? No. So this is a totally different kind of thing. This is not linear. The pattern has to be addition or subtraction. It can't be times by 2 or divide by anything. Okay? We are going to talk about this kind of pattern later, much later. But for now, you've got to look for a pattern with addition. Okay, so here's the important thing.
That's on your back side, guy. Right on the top it says, it is a linear function if you want to write everything that's underlined and in bold print.
Okay, so a table is a linear function if, as x goes up by adding the same amount, so in both tables I showed you, we did +1 each time, y also changes at the constant rate. Right? And by changing at a constant rate, what we mean is you either add the same number over and over or subtract the same number. If y doesn't change at a constant rate, then you have a non-linear function. In other words, if you drew it, it wouldn't be a line. Okay, so what we'll do is we're going to go through some tables, and all we're going to do is look at the table and figure out, is this table linear or not? And we're not going to need a picture. Okay, so we're not going to look at any pictures to do the next 4 problems. Okay, so any question on what you're looking for? What kind of pattern we have to find? All right, so let's keep that up here. Okay, and we've got some tables. Okay, now some of these tables are going to represent linear functions. Some of them will not. All right, so the first 2 things you got to check. First, make sure the x's are going up consistently. Okay. In that first table, are the x's going up by the same amount each time?
Yeah.
Yep, what are they going up by each time? Plus 3. Plus 3, plus 3, plus 3. All right, so pass the first test. Now the second thing is make sure y is also changing by the same amount each time. And it has to either be addition or subtraction. Either one is fine. So how do you get from 36 to 30? Subtract 6. Now, that has to be the pattern every time. If it is, we've got a linear table. If it's not, it's nonlinear. How do you get from 30 to 24? Subtract 6. And how do you get from 24 to 18? Subtract 6. So it did pass the test. Y changes at a constant rate, which means this would be what kind of function if you drew it? This is linear. Yep. So linear. Okay, any questions on why table A is linear?
Guys, I know it's a little bit further away, because Mr. Hager did the double speed angle. Just in case you get, because it's blank on your thing. So in case you miss, for example, A, here's your numbers.
Yeah, I'm going to look at example B. I'm not even going to look at the y values yet, just the x's. 1, 3, 5, 7. Are we going up by the same amount each time? Yep. What are we going up by each time? Plus 2. So is that enough information? Am I linear? I don't know yet.
So far, we are.
So now we have to look at the y's. How do you go from 2 to 9? You add 7. Okay, so do we know if we're linear? No. Okay, if I didn't show you any more information, you don't have enough information to figure out if it's linear or not. If it's linear, how would you get to the next number? You would have to add 7 to 9. So what should the next number be if this is linear?
16.
It should be 16. If it's not 16, then it's not linear. Okay? To get from 9 to 11, or sorry, I just gave you the answer. To get from 9 to 20, you added 11. Not linear. And then to get from 20 to 25, what did you add? Yeah, this one's all over the place. So we did not add the same value each time. So what should I write for my answer? Non-linear. Okay, so take a second and copy down example C. and see if you can figure out if that's linear or nonlinear. If you ever got really stuck, you could take graph paper and draw this. Okay, but that's going to be a long way to do it. Okay, so take a second, see if that comes out linear or nonlinear. All right, so Antonio, you raised your hand. You think you got the answer? Can you walk me through it before you just give me the final answer?
First I did accuracy works, and it goes from 0 to 1, 2 to 3, and that's just adding 1 every time.
Okay, perfect. So the x's are consistently increasing by the same amount. Okay.
And then y, 3 to 5, 7 to 9, which is increasing by 2.
Yep, that's an add 2 each time. And so now interpret that.
It's linear.
That's linear, yes, because he increased by plus 2 each time. Perfect. Okay. Now, if it's linear, then that means there must be an equation that looks just like this, that would go through all those points. There must be an equation that has a certain m and a certain b, that if you pick the right numbers, it would go exactly through all the points in that table. Right? And that's something we're eventually going to figure out. You guys want to see something on the graphing calculator?
Sure.
All right, I'll show you something. Okay, just watch what I'm doing here. I'm going to type all these points into this table. I got 0, 1, 2, 3 for my x's. 0, 1, 2, 3. Okay, and I'm going to type in my y's. I got 3, 5, 7, 9. 3, 5, 7, 9. So basically what I did is I just typed I typed this whole table into the calculator. Okay, and I'm going to show you a picture of what it looks like. Now we already said it's linear. So what should it look like when I graph these points? They should all be in a what? They should be in a straight line. Let's
I don't know how you control that so easily.
Oh, a lot of practice. Don't worry too much about what I'm doing. 4 points. Does it look like they're all in a straight line?
Yeah.
Yeah.
It's not as cool as I thought it would look.
It's not as cool as you thought?
Yeah, it's not as
All right, I got one more thing. Maybe you'll think this is cool, maybe you won't.
okay.
All right? I told you that there must be a line that goes through these points, right? Do I know the line right now?
Yeah.
Do I know like the equation or do I know the formula for this table? No, all I know is the table. Watch what I can do. Okay?
Maybe right overrun.
I could figure it out by hand, yeah, we definitely could. But let me show you what I can do. The equation that would go exactly through those points is y equals 2x plus 3.
I got excited and
Well, I got one more thing. I'm going to draw it. And I'm going to show you. The calculator figured out for me the exact line.
okay.
Now that's cool, right?
Yeah.
So the calculator figured out the formula for this table for me. Okay? That's one of the things you can do. And not only can the calculator figure out the formula if it's a straight line, the calculator can figure out the formula if it gets a lot more complicated than a line.
I want to see that.
We'll save that for a little later. I got to keep something in my bag of tricks here. All right? So you guys don't have to know how to do that, but I'm just showing you technology can figure out the formula for us. Okay, let's look at the last one, part D. Okay, do we have a pattern in the x's? Yeah, I'm adding 1 each time. Okay, now my next question, no explanation yet. All I want is a yes or a no. Is there a pattern in the y's?
Yeah.
Yes, there is.
Divide by 2.
There is a pattern in the y's. What is it?
Divide by 2.
It's a divide by 2. So we're dividing by 2. Now, is that linear?
No.
No. This is non-linear. Now, the fact that we did divide by the same number each time tells me something. Okay, I do know what this is. Anybody want me to tell you what it is? Nobody wants me to? Oh, I won't tell you what it is. Never mind. Oh, now you want to know. This graph right here, it's called exponential. Okay?
It's a big word. I'm gonna forget.
Exponential.
Tomorrow.
We'll remind you in like April or May.
Oh,
It's a graph that would end up looking like this if you drew it. It would have a curve to it.
I don't know why, but that actually made me like really happy. Kind of.
You like that curve? Yeah?
A little slow.
Okay, but bottom line for you guys, just make sure you know that it is not a line.
It was oddly satisfying.
All right, so what did Mr. Roy say earlier? That the equation of a line is always written how? It was y equals, and I showed you an example on the calculator too, mx plus b. Anything like that.
Is that, we write it down?
I think you already did in the first page of notes.
No.
Oh,
Okay, so I'm going to show you things that are not lines. Okay, and maybe I'll show you one of them on the calculator just to see it. Okay, square roots. Things with square roots are not lines.
so excited.
All right, so let me type in something like that. Okay, I'm going to type in exactly what Mr. Roy wrote. Maybe. Second, square root x. Watch when I show you a picture of a square root. Is that a straight line or does that have a curve to it? It has a curve.
I was excited and I get a line.
Well, that one's
I
curved.
thought it was going to be a giant loop or
No.
something.
Just a slow kind of curve like that.
We will get one of one of these examples.
Really?
Variables in the bottom of a fraction. 2 divided by x. That's not a line. Let me show you what that looks like. This one might be a little more exciting. 2 divided by x.
I'm done getting excited.
Is that-
I'm done getting excited.
Is that a line?
I did that.
No.
Definitely not a line.
It's pretty. I was like, I'm done getting excited.
So-
I did that.
Anytime you put a variable in the bottom of a fraction, it causes your picture to not be a line. Third thing, put a variable in the exponent. Okay, put a variable in the exponent, like 4 to the x. Okay, this one's not quite as exciting, but you'll be able to see it's definitely not a line. Okay, it's kind of starting out flat, and then it curves up.
That still made me happy.
Is that a line? Nope. So variables up in your exponent, no line. And if you put variables with exponents other than a 1, like a 2. Okay? Does anybody know what this one looks like? Like a what?
A circle?
Not quite like a circle. It's going to have a curve to it. Let me show you.
Sorry, that's what we've been waiting for.
Really? I'm so excited.
Actually, oh my gosh, thanks, Ashley.
It's gonna look sad.
That's all.
So this last one, that's what
I
it, that's
thought
what it
we were
looks
gonna
like.
do a giant loop too.
No, I'll show you some interesting graphs later after. If we have time at the end, I'll show you some really interesting ones. Way more interesting than anything I just showed you.
Really?
Oh yeah.
I'm so excited.
I'll draw a flower for you.
Really? Oh my god, I'm excited.
All right. So you guys understand all these types of things are not linear functions. Okay? You don't have to know what they actually look like. You just have to know that they are not lines.
You'll have to call it a special name for them. Let's show you what. Let's show you why. If people aren't done copying those, why don't we just scroll all the way down? Because they don't have any of those, and they can just copy them all right now. So guys, just make sure, remember, it goes down, then A, B, C, D, then E, F, G. So he's gonna write those in on your notes.
So now, looking at this equation, I want to know, would this be linear?
So basically, looking at those rules we just gave you guys, and if any of those situations pop up that we just gave you, I think there were 4 of them. If any of those show up, that makes it not a function. Obviously, it's non-linear. If you don't have any of those, you're good. It'll be linear.
Does it have
Now you bring it
does it
back.
have a square root?
No.
No. Does it have a variable in the bottom of a fraction?
No.
How about an exponent on a letter other than a 1?
No.
And how about an exponent that's a letter? No. So this is linear.
Now you bring it back.
Yep.
That's not even funny.
How about B?
Hilarious.
Is B linear or non-linear, and tell me why?
Non-linear. It's not
Non-linear.
Non-linear, how come?
square root.
Yes. Non-linear because it has a square root. How about 3 to the x?
No.
No. Non-linear, it has a variable as an exponent. All right, how about
No.
2 over x?
No.
Why is that one non-linear?
You really should give us the
Well, fractions are okay,
No, it hasn't.
but what about the fraction? Can't have the variable where in the fraction? In the bottom. So that's non-linear.
You know, so far this is telling me you have a problem against linear fractions, because so far it's 3 against 1.
All right, let's look at this one. What would be, if you were going to simplify that, what's the first thing you have to do when you have a number on the outside and parentheses next to it? What property is this? Distributive. What's 6 times x? And what's 6 times negative 1? Now somebody remind me, what was the form of something that's linear? Y equals mx plus b. Is this one, and it could be plus or minus, is this one in that form? Yes. That is linear. Okay, so even though it didn't look linear at first because we had these parentheses, it is. Okay, how about the next one? X squared minus y. Why? We don't have a variable as an exponent.
Oh, it's because it's a 2 instead of...
We have a variable with an exponent other than a 1. Non-linear. Okay, how about G?
It is.
If you're looking at this, what's B in this case? B is 9. What about M?
It's 1.
1.
You have that invisible one.
The invisible 1. So what is this one? Linear. Okay. And I think we have an H.
Yes.
Is that one linear?
Yes.
No.
Because it doesn't have the...
It's so...
Well, what could you put? It doesn't have the B on it, so you could put plus what? There's nothing there. Okay, and I'll give you a hint. Whether you put the X in the top or in front like that, these are the same thing. That and that. There's no difference. So, is that linear? Yes. Okay, so I think Cy noticed that there were a lot that were nonlinear, and that's because there are a lot more things that are curved than are straight. Okay, so homework tonight.
Guys, let's stop waiting, let's stop waiting, you're gonna have time. This is Mr. Hager.
You know what I just thought of? I'm listening.
Okay, so homework tonight, okay, first part of section 3.2. Tomorrow, second part of section 3.2, review for the test on, what day is our test? Thursday.
Remember, if it's gonna be a problem for you to print your reference sheet off of Google Classroom at home, bring your Chromebook tomorrow.